Be looking at parametric equations. Basically, when we study parametric equations, the idea now is to bring a third variable into our problem, into our equation. Basically, this extra variable is going to be the letter t, which is going to represent time. So in a lot of instances, basically we can see how time affects our equation, and it's going to affect both the x-coordinate as well as the y-coordinate. So basically time is affecting our values both horizontally and vertically. So what we're going to do is actually create two equations that represent x and y. X will be represented by f of t, and y will be represented by g of t. So in terms of the ordered pair, what we're finding is that the point xy is now modeled with the point f of t and g of t for x and y respectively. So x represents f of t, and y represents g of t. So time is going to affect both of these variables here. So as we take a look at our first equation, you can see that our parametric equations are, for our first example right here, they're given by x of t is equal to 4 sine pi over 2t, and y of t is equal to 8 cosine pi over 4t. We can see also that there is a domain restriction to have time go from 0 to 8, and it makes sense that since we're dealing with time, that it starts off at 0, because t equals 0, you start from the very beginning, and then we're going to go to 8, in this case 8 seconds. Okay, so what we're going to do is now build a table. You'll notice now that our table is not just a typical xy table. We have another variable here, that variable t, that's going to affect both x and y. So let's go ahead and plug in the value of t into both of our parametric equations. So we're going to start off with the x value. When we plug in 0, we'll get 4 sine pi over 2 times 0. Since pi over 2 times 0 is 0, we're going to get sine of 0. Sine of 0 is 0, and 0 times 4 will give us 0. We can do the same thing for y. So now we're going to put the t equals 0 into our y equation. So t equals 0. So 0 times pi over 4 is 0. Cosine of 0 is therefore going to be 1, and 1 times 8 will give us 8. So that tells us that at t equals 0, we're going to get the new order, or we're going to get an ordered pair of 0, 8. We then can go ahead and proceed and finish off the rest of the table here. Okay, so sorry, my eraser's not working. Okay, so anyway, we plug in 1, so we're going to get, let's see, I don't know why my eraser's not working. Okay, so we're going to get t equals 1, so 1 times pi over 2 is pi over 2. Sine of pi over 2 will give us 1, and 1 times 4 will give us 4. When we go over to the y value, we'll have cosine of pi over 4 times 1, so that's just cosine pi over 4. We'll get root 2 over 2 and times 8, so we'll get 4 root 2. And if we actually calculate that value, 4 times root 2, let's go ahead and find that. 4 square root of 2 is the value of let's call it 5.66. So we get 5.66. Just like that. Okay, so basically when we plot this later on, we're going to see that we're going to plot 4, 5.66. Alright, so we'll finish off the rest of this table. At 2, let's see, we'll get 0 and 0, so this will be the point 0, 0. When we plug in 3, sine of 3 pi over 2, that'll give us negative 1, so we'll get negative 4. And here we'll get negative 4 root 2. So we'll get negative 4, I'm just going to put negative 5.66. When we plug in 4, we're going to get sine of 2 pi, and so we'll get a value of 0. And for the y value, we'll get negative 8. So 0, negative 8. When we plug in 5, we will get 5 pi over 2, that'll give us 4. And then plugging in 5 for the y, we'll get, again, negative 4 root 2. So we'll get 4, negative 5.66. Plug in 6, so you get 0, 0. Okay, go ahead and finish this off on your own as well. Okay, one more. We'll plug in 0 and 8. So we'll get 0, 8. Okay. So now what we're going to do is we're going to plot our values here. Remember that when it comes to a parametric equation, we are adding this third component, which is now considering time. So what you want to do is actually plot it from beginning to end. Since t equals 0 is where we start, we're going to plot our first point here. Keep in mind this is where you start. Okay, and from there we're going to go ahead, and this is when t equals 0. When we go to t equals 1, we'll go to 4, 5.66. We'll put a point here. This is when t equals 1. Then we'll go to 0, 0. This is t equals 2. Then we'll go to negative 4, negative 5.66. That's t equals 3. Then 0, negative 8. 4, negative 5.66. Oops. Negative 5.66 right here. 0, 0, negative 4, 5.66. Okay, so when we graph this, remember, we're going in order. We start at t equals 0. We're making our way this way. Draw your arrows to show the direction in which you're going. When it comes to a parametric equation, the parametric equation is showing you the path that the function is taking, or rather the equation is taking. So draw your arrows to show how time elapses as this progresses. Okay, so you're going to draw the arrows, and you'll see that it's actually cyclical, so it's just going to keep repeating itself just like that. Okay, now the reason why we have arrows, you can see, is because it tells you where you start and the pathway that it takes, which is important, because otherwise, if you didn't have the arrows, you wouldn't exactly know where do you start and which direction are you going. We don't know, right? So you got to make sure that you are showing the arrows to show how time is progressing through our equation. Okay, that's probably the most important thing that we need to get from parametric equations, is that the idea of time needs to be taken into account, and we do that with the arrows. Okay, so as we go on to the next page, is the parametric equation a function? Well, we actually saw it wasn't, right? Because we saw that basically this equation did not pass our vertical line test. It was that figure 8 that we saw. The parametric equation was made up of two functions, though, right? We had the sine function as well as the cosine function. So they are made up of two functions, but put together, they are not a function. Remember that what this shows us is that in terms of how the skater was moving both horizontally and vertically. So as time changes, basically as time changes, both horizontal and vertical movements need to be considered. Okay? Sorry, my pen is not really working very well. So horizontal and vertical movements are considered, and so that's why we have the two different equations. Okay. So keep in mind that both of those horizontal and vertical components are with respect to time. So time is the big factor with parametric equations. All right, so for the rest of these notes, it's basically just a review of, or just more practice of what we had just talked about. You can see with this example here, our parametric equations are made up of x and y, and what we want to do is, again, build a table where you have time, and you also need to consider both the horizontal, in this case, root 2t plus 1, as well as the vertical, which is 4t. And what we'll do is we'll just make a set of values, x, y, that give us the ordered pairs for each time. All right, so let's go ahead and plug some numbers in. You see that the domain says that time starts at 0 and goes forward from there. So we'll plug in 0. When we plug in 0, we're going to get 0 plus 1, so we'll get 1. Here we'll get 0, so we'll get the point 1, 0. Then as we progress further, let's say we go to the t-value of 1. We're going to get root 2 plus 1. Root 2 is what, 1.4, so we'll get 2.4. And then here we'll get 4, so we'll get the point 2.4 comma 4. When we plug in 2, we'll get 2 plus 1 is 3, and then we'll get 8, so we'll get the point 3, 8. All right, at this point, I think we're going to go off the page, right? You can see that 8 it's increasing pretty quickly. But just to make sure that we have more points to make sure we see what is happening with the graph, what I'll do is I'll plot some more values. Let's say that we, let's do the value of 1/8 actually. So if we do the value of 1/8, we'll get 2 times 1/8, which is 1/4. Root of 1/4 will give us 1/2, and 1 plus half will give us 1.5, so 1.5. And then when we plug in 1/8 into the y equation, we'll get a value of 1/2, so we'll get 1.5 comma 0.5. And let's just do one more for good measure. Let's do 1/4. If we plug in 1/4, 2 times 1/4 is 1/2, so we'll get root of 1/2 plus 1, and that will give, let's see here, let's not actually do 1/4. That's not giving us a nice number. Let's erase that. Sorry about that. Let's just do a different number. Let's see. What number will work nicely? How about if we actually do 1/2? That way it'll cancel with the 2. So if we plug in 1/2, we'll get 1. Root 1 is 1. 1 plus 1 will give us 2. That works better. Okay. When we plug in 1/2 into 4t, we'll get a value of 2. So this will be the 0.22. Okay. So again, let's go ahead and plot these values. 1, 0. And remember that what I did was I actually took some values that were in between 0 and 1. I'm going to go ahead and plot those first. So 1.5, 0.5 will be our next point. 1.5, 0.5 right there. And then we have the 0.22, so 2, 2. And then we can go on to now look at when t equals 1, we'll be plotting 2.4, comma 4. So 2.4, comma 4. And then our last point would be 3/8. 3/8. There we go. Okay, so you can see now that as we follow the trajectory of our parametric equations, there it is. There's the arrows, right? We're showing the arrows. And so you can see that it kind of takes on the shape of, kind of looks like a parabola, right? So basically you show your parametric equations with the arrows. You've got the graph there. There we go. Okay. All right, so what we're going to do is we're going to focus on this problem still, but we're going to look at it in different ways. The first thing we're going to do is see how we can actually use a graphing calculator to also observe the same results. So get out your graphing calculators and go ahead and follow along. Okay. So what we're first going to do is in our graphing calculator, step 1, we're going to set the mode to its parametric format. Okay. I think I spelled that wrong. Parametric format. Okay, and so let's go ahead and go to our graphing calculator. And I'm going to push mode, the button next to second. And we're going to go to the 4th line down, and then we're going to select parametric. My calculator is, I think, on the older side. You might actually see the full word parametric there. Go ahead and push enter to select parametric. Now when you push y equals, you'll see it's not just the y1, y2, y3. Now the parametric form gives you both x and y in terms of t. Don't forget that you can see here it's with respect to t here. And what we're going to do is enter in our 2 equations that we saw. So as we take a look at our example again, remember we're graphing this, this parametric equation here. So x equals root 2t plus 1, and then y was 4t. So let's go ahead and type that in. Root 2t plus 1, so square root of 2. Now the variable button, you'll notice, has xt theta n. So in terms of its parametric form, now you actually see the t. So we have square root of 2t, and then we had plus 1. And then the y equation is going to be 4t. So we'll plug in 4, push the variable button, which is time, t. Okay, and then now as we take a look back at our notes, what we'll see is that we want to make sure we understand the viewing window. Okay, so as we go to the viewing window, I'm going to push window next to y equals, and now you're going to notice it's a little bit different from what we've seen before. You used to start off with x min, x max, x scale, y min, y max, y scale. But you'll also notice that there's this extra component that has the time variable in it. We're saying that time starts at 0, that's the t min, and we're going to a t max of 6.28. So it's going as far as 6 seconds, if you would like to call it that, right? 6.28 seconds. And then the t-step means how many times are we going to break up the interval of time. In the case that we saw in our example here, we started off having intervals of 1 second, but I felt like that was a little bit too large of a gap, because the 1 second marks, we had the 1, 0, but then at the 1 second mark, it all of a sudden jumped all the way up here, and we were leaving quite a bit of a gap to really not get a full accurate graph there. So one thing we can do is shorten that time interval, the t-value. So in our graphing calculator, that's what this stands for, the t-step. It says 0.13, so it's going for every 0.13 of a second, you're going to find another value, basically. Okay, and then we have the x-min, x-max, and so on. Let's go ahead and adjust the x-min and x-max while we're at it. Let's just go ahead and say that the x-min is 0, and let's do the x-max, let's go as far as 5. On our graph, we didn't go very far. And then the y-min, -1, yeah, that's fine. And then y-max, we need that y-max a little bit higher, don't we? Let's say that we have a y-max of 10. Okay, so when we graph that, there's our graph. Oh wait, sorry, I'm sorry. I forgot to mention about the t-step. Let's look at the t-step. Right now, our t-step is at 0.13. What I would like for us to do, actually, is in example 2, not only are we going to confirm our graph, which you actually just saw, but I also want you to experiment with different t-steps. So try t-step values of 0.05, of 0.1, 0.5, and 1. I think that'll give us a broad range there, okay? And I want you to observe what happens to our graph. So I'll let you do that on your own, okay? And then you can go ahead and list your results right here in example 2, okay? So just play around with this t-step and see what that does to the graph, okay? All right, so now let's go on to the next page. Again, you can, this is a video. Feel free to pause and work with the graphing calculator, find your results here, and then we will continue on to the next page. All right, so in example 3, once you've unpaused, what we're going to do is take a look at how our graph can be represented in its rectangular equation format as well. Remember that the parametric was really just adding that extra component of considering how time affects your equation. So what we're doing is we're removing the time element and just turning it into just a basic equation. As you saw in the graph earlier, you can see, what does that look like to you? It actually looks like a parabola, right? It's got a parabolic movement to it. So the path is a parabolic movement. And what we're going to do is actually ensure or verify that this is actually a parabola. So the way we can do that is actually get rid of the variable t. Well, our equation was x equals the square root of 2t plus 1, and we also had y equals 4t. And basically, this is just a system of equations. So what we can do is actually just put one equation into the other. The way you can do that is by isolating the variable t. So t is basically y over 4. Since t is y over 4, you can put that y over 4 into your other equation. So x is equal to the square root of 2 times y over 4 plus 1. Keep in mind that since we're trying to solve an equation basically in terms of y, we are isolating y, so let's move the 1 over, right? And then we're going to get x minus 1 equals the square root of y over 2. We square both sides, okay, and let me actually move this over. We're going to square both sides. And in doing so, we'll get y over 2 is equal to x minus 1 quantity squared. Bring that 2 over, and you can actually see, oh, look at that right there. We have our quadratic equation, right? This is a quadratic equation. And it's actually given to us in vertex form. What's that vertex? Well, you can see that it's shifted to the right by 1. We have a y value of 0, so we can see the vertex is at 1, 0. Taking a look at our previous graph, oh look, there it is, right? It's got the vertex at 1, 0. If you were to see that parabola, you would actually see the other side on the left, but keep in mind that because t is greater than or equal to 0, that's why we actually didn't see this part of the quadratic in our parametric equation. Okay, so that's what we're seeing here. So that's why this quadratic equation, now we actually see, based on the format of it, that x, the domain value, is x is greater than or equal to 1. Okay? All right, so why do we have the parametric equation then, if we can just see it in its rectangular form? Keep in mind that what the parametric equation is for is really to add that third component, that time variable. All right, so the reason why we have parametric equations is because parametric equations allow us to describe movement. So they are useful in describing movement. Okay? And not only that, but because of the movement, it actually shows you the direction of the movement. It shows you how a graph is supposed to move. Otherwise, if you don't have the variable of time, you don't exactly know where you start, where you end, which way you're going. You can go in either direction here, right? So that's why we have parametric equations to show the curve, show the movement of it. Okay, so it's not only used to describe movement, but also it shows you directed movement too. It shows the direction, so it shows directed movement. Okay. All right, so here are two examples for you, example 4, and I will actually just leave it to you to graph those parametric equations and discover what kind of graph it looks like, okay? As you graph that, go ahead and build an XY table. I actually want you to do it by hand. Actually, sorry, not an XY table. You're building the TXY table, right? Okay, so build a T, X, and Y table so you can see the movement, and do the same thing for the other side as well. Okay, all right, now you're also going to find the rectangular equation of them, so go ahead and practice what we had just seen in example 3 by rewriting the parametric equation into its rectangular equation. And I'm just going to go ahead and work with this one with you because this one can be, I'd say, a little bit challenging. Okay, okay, so you're going to graph it, understand what this looks like, okay? And what we're going to do is we're going to go ahead and say, okay, so since x is 2 cosine t and y is equal to 3 sine t, we're going to work with this a little bit differently. If we divide both sides by 2, and over here divide both sides by 3, you'll see that cosine of t is equal to x over 2, and sine of t is equal to y over 3. So this is going to be a little bit different, right? We're going to, once you have understood what this graph looks like, we're actually going to do a play off of trig equations. We know from before that sine squared plus cosine squared is equal to 1. So just plugging or substituting our equations in now, we can see that we get y over 3 squared plus x over 2 squared is equal to 1. And in turn, this is going to give us basically x squared over 4 plus y squared over 9 equals 1. So there is your rectangular equation. And I would like for you to go ahead and see, does that match up with whatever that graph looks like? Okay? All right, so remember, finish this up. I don't want this video to be too long, so that's why I'm just going to close it off here. Make sure you finish the rest of the notes on your own.